Our next talk is remote, and I'm hoping the technology can support us there with David Slater. And David Slater is a well-renowned risk expert in this sort of area. And he's worked for in pollution, for HSE, for a whole range of things, and is now at Cardiff, I believe. David, are you on the line? Can we?
Well, thank you for the introduction, and thank you for the invite to this very interesting session. John Holmes, that was very, very impressive, and we must get together afterwards because there's a lot of stuff I wish I'd known before I wrote this talk. But anyway, safety critical systems are a very interesting concept. Exactly what is safety critical in a system is a moot point. But one of the things I want to try and encourage you to think of is a little wider than just electronics and IT systems, but in fact to consider whether decisions under uncertainty are actually made by humans, and that's a prima facie safety critical task. So it's being made by a safety critical system, which is in fact a human. So I think if we extend our system definition to the human, I think we may get more closely allied to the problem. But anyway, that's the change. So I'm not looking at the hardware, I'm looking at the software, and the software, which is the human being. So normally and we saw it was very impressive the way in which that emergency was handled. And normally we do handle emergencies quite well. So we have plans, we have procedures, we have exercises. And for normal emergencies, we normally get away with it, to quote the number 10. And we get away with it because we know how it works. We designed it. We know intimately what can happen, etc. And of course, if it doesn't behave as predicted, then we've got these excuses, acts of God. And Black Swans is a very good face saver. We couldn't have known because nobody knows. But that excuse, I think, has a little more to it than just the Black Swan. In fact, it was used by Secretary of State Rumsfeld for the Iraq War. In other words, the Rumsfeld unknowns, things which we're unaware of and don't know and therefore couldn't possibly be responsible for. But that then he gave this categorization of knowledge in terms of these 4 quadrants, which are now quite popular. So you have the known knowns, the things that we all know. And then you have the known unknowns, things that we're aware of that we don't know, so limits of our knowledge. And then there's the below the iceberg, the things which catch us out, things which we're unaware that we know, but we're unaware that we know them. And the last thing, which is the black swans, the things which we're unaware of and we don't know and couldn't possibly know. So Tallis Black Swan has gone into the history books, and it's now everybody's talking about black swans, and everybody's definition of a black swan really suits the case in which they're trying to develop it for. So an unpredictable event that's beyond what is normally expected of a situation with potentially severe consequences. Fine. And one of the things that you always find is that after the event, of course, it was quite obvious what happened. So therefore, it wasn't a lack of knowledge. But the black swan is a kind of philosophical discussion, and we're talking to engineers, safety critical systems. We've got to be a lot more focused on exactly what we're talking about in terms of a black swan. So what we can look at then is classifying systems in terms of their complexity, and we've got a range of complexity definitions that we can use. And if we try and sort of correlate with the Rumsfeld quadrants, then we've got the simple systems. These are the simple systems. They, we've seen them a million times. It's something we can draw out. We know exactly what the schematic is. We know exactly how it works. From the risk analysis point of view, the relationship between cause and effect is clearly demonstrable, well known, and everybody, it's unambiguous. And then you've got the second level of system complexity, which is a complicated. Now, complicated is still if you like, predictable if you know the rules. And the problem with the complicated is you don't always know all the rules at your level of expertise. So the designer may know what it's all about, but the guy that's operating perhaps doesn't have the range of expertise. That's complicated. It's still predictable. It's still, if you like, reliable. We can still do risk assessments on it because we know all the behaviors involved. And then we get to the complex. Now, the complex is this level where, if you like, the easy way of defining a complex system, I think, is anything that you have humans involved in, which these days accounts for quite a few of the systems, because complex system, humans are essentially unpredictable. You can't just do a risk assessment on a human and come up with some bathtub curve for humans, attention, etc., because everybody's different, everybody's individual, and they're complex systems in themselves. So anything that involves humans, anything that involves systems that we're not entirely clear about is complex system. And then you have this last, the Rumsfeld unknown unknowns, the black swans, the chaotic. Here's where you have a situation which is really unstable. You don't have time to experiment. You don't have time to probe. You just got to act. And for example, an IT issue, basically just shut it down, reboot it, perhaps. And then I've added in this last scenario, this last category, which is the disorder. In other words, anything that doesn't fit into your framework then is something which is unique, it's unheard of, and you should treat it separately and quite with kid gloves, as it were. This is something which you really don't know what's going on. So what's happened is that this essentially range of complexity, you can actually turn that into the kind of Black Swan based ideas, which you can get over and get over quite quickly in terms of these what we call signology, which is to use a quick cartoon almost picture of what's going on. So for simple systems, then everybody knows, everybody understands, but for some reason we neglect it. These are the typical elephants in the room: smoking guns, the cladding fire at Grenfell, the PPE in COVID-19, the masks, etc. Things which everybody knows, but for some reason we neglect. And then you have the complicated situations, which are sometimes called gray rhinos. This is the knowables, but not by us. And we'll come to some examples later on which reflect this. And in major industrial disasters, this actually is the most common cause of disaster: the Piper Alpha, Bhopal, Flixborough, Longford. Gray rhinos is a term that some people use to categorize this. It's not quite complex, it's not quite simple, it's a little bit more complicated. And then you have the so-called gray swans. Now, these are complex systems, and we're aware that we don't know it. There are boundaries and, for example, limitations of knowledge, but we're actually going to disregard it. We're allowed, the system allows us to disregard this boundary, this limitation of knowledge. And these are typically beyond design events in the offshore and nuclear systems. Fukushima, for example, climate change is a gray swan. We know it's there, but we basically are allowed to neglect it if you're in politics. Then you have the real black swans, the chaotic. That's the things we're unaware of, we don't know, the unknowables, etc. And these are really situations where we need to be very concerned if we're risk analysts. We're in the unknown situation. Disorders, well, I think anytime you get involved with politics in situations, then you've got a system which is totally unpredictable and not necessarily rational and not necessarily solvable using our classic techniques. So you have a signology which we can use, and we can use to combine all these things together to give us a decision framework. And this is categorized into the what's so-called Cynefin framework, which is very popular with the European Union disaster response teams these days, which is basically, first of all, know your system, know where you are, know what the background is, and then you can start to frame your decisions based on which sector you're in. And we've got our signology and our Rumsfeld unknowns all brought together into a nice picture. So which sector you're in depends on how you respond. And it's one more complication, which is that you have a thing called Rasmussen drift, which actually shifts between quadrants. So you may start in one quadrant, but actually in reality, you may drift into another. In normal life and operation, any situation which is being delivered, if you like, has a range of outcomes, and nothing goes precisely as it's designed to go. So the planned outcomes are more or less achieved, but sometimes you do better than you expected, sometimes you do worse than expected, and sometimes you can have a combination of circumstances that can push you over the line. And Rasmussen pointed out that actually once we're in this, if you like, a range of behaviors, we tend to push the limit, the envelope, away from economic failure or away from unacceptable workloads. And this tends to push us towards a boundary, which is the boundary of safety. And once we cross the boundary, of course, then here be dragons. The normal variability pushes us into a different sector altogether. So let's look at some quick examples. One of the talks we're going to be seeing later is Bunsfeld. Now, Bunsfeld was a very simple emergency situation. And we heard that before. The people tend to rely on instrumentation. And when you're sitting on the midnight shift filling tanks, which take an awful long time to fill, you tend to basically just go and get a coffee and wait until your high level alarm goes off, and then you can actually come and take over and stop the filling. If your high level alarm doesn't work, then you're in real trouble, because the petrol will just rise up the tank and come out of the top. And the Black Swan in Bunsfeld was actually not the thing that caused it, which is this common overfilling scenario, but the actual behavior of the petrol vapor cloud that was formed, which formed an unconfined vapor cloud, which we still have difficulty explaining. So a simple situation can lead to a black swan. More likely, though, is the complicated situations. And at Flixborough, for example, now Flixborough was an example of a workforce trying to get around a problem. They had a reactor. They had a series of 6 reactors. One of the reactors developed a crack. They took it away and replaced it with a pipe. You had a difference in level, which meant they had a dogleg in the pipe. And once these were pressured up, it was between 2 bellows, which allowed for expansion between the reactors. But with no reactor there, you had a floating pipe subject to forces. And as the engineering syllabus tells you, this develops a force which buckles the pipe, and the bellows can then, because they're only thin stainless steel, they can burst. So you had a situation where the engineer who designed the system knew very well that you should never have a pipe between 2 bellows. The engineers on the ground actually trying to get back into production, they just basically were working around. So you had a situation where the hazard was knowable, was known, but not to the people involved. Same with Longford in Australia, where you had a gas plant taking gas from the offshore fields. They use the Joule-Thomson effect to reduce the temperature and take out the higher fractions, the methane, butane, etc., and leave you with the gas. And because of the low temperature, you have a part of the plant which is designed to take low temperature, and then you have the rest of the plant where you needn't bother to have the expensive steel. You can have ordinary steel, which of course is subject to brittle fracture. And as happens, you've got a cold liquid into the high temperature part, failure. Bhopal, reactivity of water, something which was known, but actually not to the people using it to flush the plant. Piper Alpha, you had a rise of flame, which was basically predicted to be 400 feet when we did the risk assessments. This was basically known, but actually only until we saw the flame on the Piper Alpha videos did we realize it was actually capable of happening. And at Grenfell, of course, the flammable cladding was supposed to be non-combustible. So the complicated ones are fairly regularly the causes of basic problems. Complex, you have a rather different scenario. And complex is when you've got a series of things, systems, and it's the uncertainty, exactly how these systems interact, which cause you a problem. The Rasmussen drift between different areas. Macondo well from BP, for example, it was being run from London with contractors from the States. You were in a depth of water which had never been drilled before. There's all kinds of complications which nobody was actually pulling together into one picture. The beyond design basis events, for example, a 3 Mile Island, it actually was never envisaged that you'd carry out the flushing of the ion exchange columns, and that was never part of the emergency drills and plans, etc. Chernobyl, again, this was not something which was designed to happen. And climate change, of course, none of us want to deliberately set out to cause climate change, but it depends on how you define the systems. So you have a whole system of black swans, if you like, or emergencies, which people call black swans, but they aren't really. So what are the real black swans? The real black swans is where you have a change and really a change of thinking, a change of perspective. For example, when we discovered Australia, it was the Aboriginals, I think, who had the black swan problem with invasion of white men, the aliens. In 9/11, you have a black swan because you changed the whole perception of what was possible, what was expected from terrorism, counterterrorism. COVID-19, I think, could be argued as a black swan because although everybody, all the professionals were used to pandemics and there was well worked out plans to deal with pandemics, the sheer scale and the sheer complexity of the COVID-19 pandemic took us by surprise. In mass casualty events like the Manchester Arena, things get chaotic because there's too many systems involved. In emergency departments, again, you have to act, you have to deal with all kinds of things with incomplete information, incomplete facilities, etc. And in midwifery, we've seen a lot of problems with midwifery where you can't afford to get mistakes, you have to act, and the systems get very complicated. So real black swans are things which you don't expect, which you have no right to expect, and are pretty rare, actually. Take, for example, this nuclear power plant in Ukraine. We saw on the television that it actually was fired upon in the war And in fact, the Russian army took it over after shelling it. Now, I'd like to stake a bet that no PRA of any nuclear power station that's ever been built had as one of its risk cases, its design accident cases, the shelling due to an invading army. So is that a Black Swan or is that a Dragon King? And if it was a Black Swan, it's a Black Swan no more, because there are at least 3 other major nuclear power stations in that area. So again, it's a problem, it's a practical issue. Let's not worry about how many angels dance on the head of a Black Swan, but let's get into what can we do about it. What can we do about it? Basically, I was very impressed with the first speaking, the first scenario, the way they handled it. I think we have to do a couple of things. But first of all, we have to be realistic. We have to look, we live in the real world. We have to recognize reality. We have to recognize imperfections and the way people behave. Chaos happens and we can't control everything. Because we can't control everything, then we should forget about having set and absolutely rigid responses to situations. We live in a complex environment, but we evolved to survive in a complex environment. The species survived asteroid impacts, for example, which the dinosaurs didn't do. The mammals survived those. The ice ages. We're a species that's constantly adapting to a complex environment. So plan. Yeah, we have to plan. There's no excuse for no planning. But as the military say, no plan survives first contact with the enemy. But it gives you the situation awareness, gives you background. Train, yes, you need to train your people. You need to have procedures. You need to have manuals. You need to work it all out. You need to have processes. But if you think that by having these plans, training, checklists, you can cover every eventuality, then I think we have a problem. So is it robotic, automatic, plan, do, check, act, which again is a very good discipline, and we need to do it. We need to have this kind of approach, but is this sufficient is what we're asking in terms of recognizing Black Swan situations. So plan, do, check, act, absolutely, but we need to do more. What more do we need to do? Well, we need to think. And well, we think all the time, don't we? Yes, we do. Maybe we think too much sometimes, but we need to think strategically. We need to think in emergency situations. And let's look at 2 possible extensions to PDCA, plan, do, check, act. First one, I think, worth looking at is comes out of John Boyd's system that he developed for US fighter pilots, which is his OODA loop: observe, orient, decide, act. In other words, be quite disciplined about how you look at a situation, and you basically look first, what's it going, which quadrant are we in, orient, and once we have a good impression of where we are, what are the plans, what are the things which are appropriate to the situation we're in, and only then do you decide, and then you decide and act. So you have this think first, act second, rather than having the pre-thought plan. You've got to orient yourself. Klein also had the same sort of thoughts. He calls it recognition primed response. So what he's saying is the way in which you respond to a situation really needs to be primed. You need to have some kind of background that enables you to observe and orient yourself very quickly. So in fact, the decisions you're making, the acts you're making are the right ones. So it's basically being, yes. But the real question we need to ask with all these systems, which are designed to make us think logically, is the time to think logically. Because in most animals, there's a an instinctive reaction to emergency situations. And these are typically fight, flight, or freeze. And these can be entirely the wrong reactions in certain situations. Or if we take our plan, do, check, act, have we got time to read the manual? And as we saw with Solly Sonnenberg at the Hudson River, there isn't time to read the manual. You haven't got time to react. So if you're looking for the best fit to a situation, if you're in command, do you systematically evaluate all the potential outcomes you can have from this situation? Do you logically consider all the potentials, the pitfalls, and do you then choose your best fit? Well, rarely. And most people instinctively identify patterns that match with what they know. And this is what Klein calls his recognition primed decision making. In other words, there is an inbuilt ability to recognize which situation you're in. So how does that come about? How do we think? Well, one of the basic, or one of the helpful ways of looking at how we think, I think, was developed by Kahneman. He got his Nobel Prize for the psychological work on how people think. And Kahneman basically tells us that we think, actually, we don't think if we don't have to. That most of the time we operate on an autopilot, as what he calls a system one. And this system one operates automatically and quickly, little or no effort. And you actually are almost unconscious that it's going on at all. We all experience this. For example, on a Sunday morning, who's tried to drive to the store, in fact, to pick up a newspaper and find yourself driving to work and you've taken the wrong turning? And that's because you do drive almost all the time on system one. And while you only correct your situation when something tells you that what you predicted, what you expected to see actually isn't happening. And therefore system two, which is this higher level attention system, which needs mental activity, which means complex situations need to be evaluated. All that kicks in when the system one is looking out of control. So most of the time, you're working on easy things, which you recognize easy, which Kahneman calls heuristics and biases. And for example, a lot of our problems these days arise from system one. When you look at a person, meet a person for the first time, you decide within seconds what kind of person that is, whether it's a threat or whatever. You make your mind up. And this is where things like biases, the racism, which are all instincts, survival instincts, which come in because you're not really thinking, you're just letting system one, this autopilot, tell you what to do. So there's heuristics and biases, which are basically determining exactly how you respond, and particularly if you haven't got time to switch in, because system two takes more effort. It takes typically 20–30% more effort than because you've got a bigger network of neurons. It takes more time because, again, you've got to get all these circuits working, etc. So the operation system two are vital to make intelligent decisions. But they're also almost like the override situation. The other interesting thing that we ought to think about is, do we really think? In other words, how important is the conscious decision making? One of the things which brought this up, I think, is it's now 50 years ago. Libet made some experiments which are very simple. He had subjects and he basically hooked them up to an electroencephalograph and had them do very simple thing like push a button, but basically note the time on a clock on which he decided to push that button. and then just basically tell the experimenter what that time was. And what they found was that although they were conscious of pushing the button, their encephalograph showed that their brain activity started to operate almost half a second before they were aware that they were going to press that button. So awareness happened half a second after your brain is doing something, preparing you to make that decision. So it's one of the interpretations of this is that we don't have free will, that actually we're told by our bodies what to do. But I think that's an old-fashioned way of looking at it. What a better way of looking at it is that your body has these natural circuits, if you like, which predispose you to action. And you can look at this if you take a system view of the brain. The brain is a very complex system of systems, but it's evolved over time. And it's evolved over time, taking all the adaptations from sea slugs through to sapiens. For example, they're all there in all the organisms. You can see these levels develop. And it's only the very highest organisms that have these top levels, and it's only us as the king species, the key predators, if you like, who have the full facilities to do the system 2 and system 1. But the primitive brains are there. For example, sea slugs can sense light, they can sense heat. And the sensors then feed into a primitive brain, which tells the muscles to work. So you've got this basic engine room where you sense and react. And all of that is absolutely hardwired. Then you've got the brain stem, where you've got the automatic thermostats for the heart rates, the metabolism, the respiration. All that is carried out absolutely automatically in the brain stem. These systems are there ticking over, and all organisms have these systems to run their basic metabolism. And then you have these slightly more complex systems which have a midbrain, and the midbrain has the basically what is the router of the brain, the thalamus, which is able to route signals now not just automatically to the automatic systems, but has optional extras, if you like, that you can bring in. And these are, for example, the memory. So you can build up memories. You can actually store emotions connected to events, and those emotions can then use the hypothalamus to release the hormones to prepare the body, for example, for fight or flight, and it's these chemical reactions on the body that give you the emotions, the feeling, etc., which are then coupled to the memories. But it's only when you get to the cerebrum, which is the heart of the human brain, if you like, the workplace. This is where everything is brought together, everything is integrated into a picture of the perception, if you like, of reality, of the world around you. So you have a real-time picture of what's going on. And from that picture, then the cerebral cortex and the neocortex and the prefrontal cortex in particular can then decide on what action to take. If it doesn't decide what action to take, it's got a whole bunch of automatic responses which can take over. And this includes the fight or flight. So if you haven't got time to do anything, your body can tell you, just get the hell out of here. And this is fully automatic. So you have a system of systems which we can use then to interpret what's going on in the Limbit experiment. So basically what's happening then is he's sensing the environment around him, the level A, so you've got the range of sensories, and this is coming in and being fed into the upper levels. Now, you think that you're thinking what you see in perception is real time. It's actually not real time. What happens is you're looking at a picture that's come through your eyes or from your. This is what reality was a tenth of a second ago, maybe even more than that. So, what your brain does is, in addition to integrate the picture of what's going on, it actually predicts. So you're looking at a prediction of what is there, and you have to have this to, for example, to return a Federer serve, which is coming, or a player fastball. You haven't got time to think about it. It's happening in fractions of seconds. So you have to predict, and all the skills, all your motor skills, etc., are based on being able to predict what's happening. So all of this is unconscious until you actually start to think in the cerebellum, and you're aware that you're going to make an intention to press a button. And then, for example, you could say, well, perhaps I don't want to press it just yet. And your prefrontal cortex can then take over and say, no, I don't want to do it, or whatever it is. So the understanding of this complexity really needs, we need to have this, because this is what is crucial in an emergency. How do you respond? What actually are the basic drivers to how we make decisions? And humans then have this ability to have a kind of an inbuilt or a sixth sense experience, whatever you call it. They can adapt to situations. They don't have to do it by the book. They've got intelligence. And for example, at the Manchester Arena, the NHS workforce which responded was very different to the way the police and the emergency services responded. They just basically got on with it. They got stuck in. They just turned up at the hospitals, and whoever was there first took the role, and they just made it up as they went along almost. And the response was amazing. You saw the same thing with the NHS at London Bridge, where they turned up at the hospital and they just did it. They just didn't think about it. They just got on with it. A lot of what we see in industry are also near misses. This is why failure reporting is important, but actually much more important is near misses, how people deal with situations. And the way in which you're able to get away with near misses is the ability of the human, this complex adaptive system that they've got to work around situations, to see situations evolving and to head them off. So these workarounds and near misses are all abilities that we have as humans to cope with situations. And again, if you look at the Ukrainian army versus the Russian army, the Ukrainian army is working, it's small units responding, it's empowered, the units are getting on with it, whereas the Russian army, which is a control from the center, discipline, etc., you have a much different way of performing. Again, you can see this in reality. If you look at Fukushima, we all know about the Daiichi plant, which was overrun by a tsunami, but not a lot of people know that 10 kilometers down the coast is a number 2 plant called the Daini. Ichi in Japanese is 1, Ni in Japanese is 2. So you have the Fukushima 1 and Fukushima 2. Fukushima 1, you had a disaster. You had a meltdown, explosions, and contamination with radioactivity. Nobody's heard of Fukushima Daini. Why? Basically because although they were hit with the same tsunami, they actually recovered the Fukushima 2. And the way they did that was through the workers actually looking at they had the same problem. They knocked the power out of the emergency response center. The cooling power, the diesel generators for the emergency cooling powers were knocked out. So you had the same situation, but at the second plant, the workers were able to assess what the situation was, what they needed to do. They needed power from other points. They actually laid heavy cables across the plant. They managed to get them hooked up, and within 4 days, the reactors cooling was restored, and on day 5 all 4 units in the system were working again. That's all down to the way in which the crew, the people involved, responded. At Fukushima 1, they did it by the book. They responded by the book. They worked to the plans, procedures, etc. The situation wasn't envisaged. The emergency power was knocked out, and they were stuck with it. They couldn't handle it. Whereas at Fukushima 2, it's just the different people, the different team, the different responders actually use their human ingenuity to work around the problem and save the day. So what that really highlights to us is the problem of what are these safety critical systems that we're relying on. More and more these days, they seem to be computer-based. And again, I guarantee that if the Fukushima systems were on automatic AI safety critical systems, you would have had Fukushima 1 problems, where basically you have a situation where they would be, the finger on the button would be automatic, and if you replace the human agents with the AI systems, if simple systems, you might get away with it. For example, at the Buncefield situation, you could certainly have automatic systems which would override the backup systems. And you can see that with the NAT systems, where you have backup. But for simple systems and complicated systems, it works. But again, if you have more complicated, more complex, chaotic regimes, if you have pre-programmed, inflexibly biased automatic responses, you could be in trouble. On the other hand, the AI actually is very, very helpful for augmenting intelligence. On the F-35, there is almost like a brain-like system which brings all the sensory data together into a common display. This is where you really get the payoffs from AI systems. And what if scenarios are very easy to run with computer systems, which are a great help. What if I do this? What if I do that? Simulations, excellent. Decision-making, not yet. So, expert systems, not automatic override. Augmented adaptive resilience, not predetermined inflexible response. So to conclude, then, basically, what I'd like to leave you with is the importance not just of planning and theory, but the importance of actually instinct, experience, and the time for thinking. So it's Heineken training. When you're training your people, you need to reach the parts that classroom training cannot reach. In other words, put them through the drills, put them through the situations of simulation. They need to experience. You need to train these levels in the brain, which I'll take care of the half second before, in fact, you are aware you need to make a decision. The things that predispose you to situations, the biases, the prejudices, the wrong thinking, which can get you into trouble. So Heineken training. Then you need to have responsible empowerment. And again, the impressive thing about the NATS paper was how they empowered the people actually responsible for doing the. So once you know that you're responsible and you can't just pass off the responsibility higher up, then you need people behave differently. people behave more responsibly. You need leadership, not micromanagement. And again, that was distributed control rather than top-down dictatorship. We're talking about team learning. This, again, is crucial for responsible and resilient systems. Resilience, just to remind ourselves these days that there are 4 aspects to resilience that you need to respond quickly, obviously. You respond well. You need to monitor what's going on, obviously, but you need to learn. And the reason you need to learn is you build up a database so that you can start to anticipate. So it's basically get your retaliation in first. You need to have systems which recognize situations which are developing. You need to be able to anticipate problems, and this is what we're not doing. You can log and you can predict failures, but you need to anticipate the results of things which are happening in systems. So you need to build this resilience and responsibility. And to do that, the way you do that is to treat your teams as Premier League football teams. In other words, you're the coach, the teams are what are going to deliver, and if you don't on the pitch, they are the ones that make it happen. You can't make it happen for them. So you've got to treat them as Premier League teams rather than just teams of yes men. So let me leave you with one more quadrant to finish. One more quadrant. This is a situation where you've got your decision maker. Do you want your decision maker to be unconscious that he's incompetent? Or perhaps a little better, that he's conscious that there are things that he doesn't know, that he's incompetent? That's a better situation. Better still, that he's conscious that he's competent, that he can work these things out, that he knows how to do things. Or perhaps what we're trying to get to here is the best place of all is that he's unconsciously competent. His lower levels of his brain are sufficiently educated, quote unquote, trained, utilized, that actually he does the right thing because it's the right thing it's not a and particularly when he hasn't got time, the right thing is the thing that his brain is telling him to do, and it's not what he has to spend time going through spreadsheets and decision maps, etc., to work out whether or not he's right or wrong. So which space would you want your decision maker to be in? You'd want him to be unconsciously competent. Questions?
Thank you very much, Dave. That was a really, really illuminating talk there. So it covered so much, actually. Fantastic. Thank you very much. Any questions in the room? Any thoughts, comments? Yeah, we've got one over here, I think.
Thank you for that. It was really, really interesting. I've taken a lot of notes. I work in probably quite a different sector to other people in that I work within the road sector. So I'm struck by a lot of the conversations so far, and a lot of the work within this club is around organisational approaches to safety. So when you're talking about system 1, system 2 thinking, that's really salient to me. And I'm very conscious that, yes, drivers so you have an organisational Black Swan event, but you also have individualised Black Swan events. As drivers, every crash is novel and most people don't experience those day to day. So in system 2 thinking, as drivers, your fallback position is the understanding of what's been inculcated into you through 30 years ago when you passed your driving test or whatever. My question, a general one really, is if you're aware of any work that's been done which examines how much we rely on, that sort of decision-making, instinctual decision-making, in a system where humans are component parts of the system. Do you see what I mean? So, because obviously how we respond when we're component parts of the system and the system is reliant on that action, it's very different to when you're looking at it as an organizational response, if that makes sense.
Yeah, it does. again, I think when you look at situations in healthcare, it is very much about people. People are the components. It's a medical team, and they need to respond. And actually, it's very, very, very interesting. They almost have too much autonomy because, but they have to have it because they have to act. And no action is not an option, life or death. I think it's very different. In an organization, we can plan and we can design the different responsibilities. When you have a medical response team, they just have to make it up as they go along, and therefore the system one is actually much more important than system two. And this is where they're starting to realize that AI in medical systems is best used as an augmentation. For example, it's a cancer diagnosis by computer program is actually more reliable. But in an emergency situation, it's not necessarily. So all you're doing really is bringing together a best diagnosis, but actually that's only part of that particular problem. So what you've got to do is augment the system two using the computer, because the system two is the logical calculator, but you still have to retain the system one, which is the instinct, the experience, which is what John Holmes is talking about, is highly skilled, highly experienced people who made the decision, but actually couldn't write it down or couldn't logically give you an explanation of exactly why they did that, but they knew it was the right thing. So, and you get that in the medical emergency teams all the time.
Okay. Thank you, David. There's just one chat question, I think. Wendy Owen mentions that BDBA, which I think is beyond design accident, is a common feature of nuclear safety cases.
Yes, it is.
Not seen it in other sectors. Should other sectors reconsider that position?
I think the nuclear sector ought to consider beyond design basis cases. I think they're the ones that are out of step. I think the nuclear sector, to be fair, was one of the sectors that took risk assessment seriously early, and therefore a lot of their schemes are historical. And I think beyond design basis, as we saw in Ukraine, is clearly now out of line.
Okay, thank you very much. David, that was a really fascinating talk. I'm so glad I managed to get you in on this seminar.